A row of sealed canisters sits in a tunnel deep underground. The walls are not polished. They are stone. The light is low, almost amber, as if the tunnel has been built not for people, but for time itself. The camera moves backward past the canisters, one after another, and the labels disappear into shadow. 10 years pass, dust settles on the floor. 100 years pass. The lights are gone. 1,000 years pass. The tunnel is silent. 10,000 years pass, and nothing on the surface remembers the machines that brought these containers here. Then the timeline keeps moving. 50,000 years. 100,000 years. The canister is still there. The strange part is not that it explodes. It does not. It does not burn through the rock like a monster in a disaster film. It does not sit underground waiting for one dramatic moment. Its danger is quieter than that, and harder to understand. Inside the sealed metal, inside ceramic fuel pellets, inside atoms too small to see, unstable nuclei are still changing, one by one, second by second, century by century. The waste is not a bomb, it is a clock. To understand why nuclear waste can remain dangerous for thousands of years, we have to start with a scene that looks almost beautiful. Spent nuclear fuel rods glow blue underwater. They rest in deep pools covered by many meters of water, and the water is doing two jobs at once. It cools them, because the fuel is still producing heat after leaving the reactor. It shields radiation, because the fuel is still intensely radioactive. The glow can look calm, but calm is not the same as harmless. These rods once sat inside a reactor core during operation. Uranium atoms split, releasing energy and creating a storm of new radioactive products. Some of those products decay quickly. Some decay slowly. Some release strong radiation for years. Some remain hazardous on time scales that feel less like human planning and more like geology. Fuel rod taken from a reactor is not simply used up. It is a dense record of nuclear reactions. Inside it are uranium atoms that did not split, plutonium created from uranium, and a mixture of fission products formed when atoms were broken apart. The rod has stopped being efficient fuel for a power reactor, but it has not stopped being active. It is still hot, it is still radioactive, it is still changing. The first trap in thinking about nuclear waste is the word radiation. People often treat radiation as one thing, one invisible poison, one glowing danger, but radiation is not one single behavior. Different radioactive materials emit different kinds of radiation, with different penetrating power, different biological effects, and different shielding requirements. Alpha particles are heavy and do not travel far. A sheet of paper or the outer layer of skin can stop them, but if alpha-emitting material is inhaled or swallowed, the danger becomes internal. Beta particles are lighter and can travel farther through tissue, but they can still be shielded by suitable materials. Gamma rays are deeply penetrating electromagnetic radiation and require dense shielding. Neutrons are another problem again, often requiring hydrogen-rich materials or specialized shielding. This is why one type of nuclear waste cannot be judged only by whether it is radioactive. The question is, what isotopes are inside it? What kind of radiation do they emit? How much energy do they release? How easily could they enter the body? And how long will they remain active? Now the camera moves from the glowing pool into the atom. An atomic nucleus sits at the center of darkness, packed with protons and neutrons. Most nuclei are stable enough to stay as they are, but some are unstable. They contain too much energy, or the wrong balance of particles, or a structure that cannot last. Sooner or later, that nucleus changes. It may emit an alpha particle, it may emit a beta particle, it may release gamma radiation, it may transform into another element or another isotope. That process is radioactive decay. The dangerous part is that decay is not controlled by human schedules. It does not care about political terms, building lifetimes, empire lifetimes, or the memory span of a culture. It follows probability. If you have a large amount of a radioactive isotope, you can predict how long it takes for half of that isotope to decay. That time is called the half-life. But half-life is often misunderstood. A half-life does not mean the material becomes safe after that time. It means half of the original radioactive atoms have decayed. After one half, life half remains. After two half-lives, one quarter remains. After three, one-eighth remains. The curve keeps falling, but it does not instantly drop to zero. For highly radioactive material, even a small remaining fraction can matter. At the same time, a short half-life does not automatically mean low danger. A short-lived isotope can be extremely intense because many atoms are decaying quickly. It can release a lot of radiation in a short time. A long-lived isotope may decay more slowly, but it can remain a concern across vast time spans. The problem is not simply short half-life bad or long half-life bad. The problem is the combination of intensity, radiation type, chemistry, mobility, heat, and exposure pathway. This is why spent nuclear fuel changes character over time. In the early period, after leaving the reactor, short-lived fission products dominate much of the heat and radiation. The fuel is fresh out of the core, and it is dangerous in a very active way. It must be cooled, it must be shielded. Workers cannot simply stand beside it unprotected. Water pools are used because water absorbs heat and provides shielding. The scene is controlled, engineered, monitored. Years pass. Some isotopes decay away. The heat output drops. The radiation changes. The waste becomes easier to handle than it was at first, but not safe in any casual sense. After enough cooling time, many countries move spent fuel into dry casks, heavy containers of steel and concrete designed to remove heat passively and shield radiation. The image changes. The glowing pool becomes a storage pad. Massive cylinders stand in rows under open sky or inside protected areas. They look still. They are still. But inside them, the atomic clock continues. The next trap is thinking that radioactive means one danger level for all time. It does not. Imagine two clocks inside the waste. One is loud, fast, and intense. It ticks hard for years or decades, then fades. Another is quiet, slow, and persistent. It ticks across thousands of years. Nuclear waste is difficult because both kinds of clocks exist together. Early management must handle strong heat and radiation. Long-term management must handle isotopes that persist long after the first intensity has faded. Some commonly discussed fission products, such as cesium-137 and strontium-90, have half-lives of about 30 years. That is long compared with a human emergency, but short compared with geological disposal. After several centuries, much of their original radioactivity has decayed. They matter greatly in the earlier centuries. They shape heat, shielding, and contamination concerns. Other radionuclides last much longer. Plutonium-239 has a half-life of about 24,000 years. Some other long-lived isotopes can persist on even larger timescales. Their radiation may not dominate the early heat the same way short-lived products do, but their persistence makes them part of the deep time problem. The camera pulls back from the atom to the human body. Radiation damages living tissue because it can ionize atoms and molecules. It can break chemical bonds. It can damage DNA. Cells may repair some damage, but not all damage at high doses. Radiation can cause acute injury at lower doses. It can increase long-term cancer risk. The danger depends on dose rate, radiation type, exposure duration, and whether radioactive material is outside the body or inside it. A sealed canister underground is not dangerous in the same way as radioactive dust in lungs. A fuel rod in a shielded pool is not dangerous in the same way as dissolved radionuclides entering drinking water. The science always comes back to exposure pathway. Where is the material? What barrier contains it? How could it move? How could it reach people or ecosystems? This is why nuclear waste management is not only nuclear physics, it is engineering. It is chemistry. It is geology. It is time. Now the image becomes mechanical. A thick shielding door slides shut. Behind it, fuel assemblies are handled by machines. Workers stand at distance. Instruments measure radiation fields. Everything is designed around a simple fact. The material cannot be treated like ordinary industrial waste. You do not solve this by throwing it away. There is no away that means outside physics. The first goal is control. Spent fuel is kept in water pools long enough for decay heat to drop. The water must be maintained. Cooling systems must work. The fuel must remain shielded. After that, dry storage may use steel canisters and concrete overpacks. Air moves around the container and carries heat away. The fuel remains sealed and shielded. This stage can last decades. It is a bridge between reactor operation and final disposal. It is not the same as the final answer. It is a way to keep the waste stable while heat and radioactivity decrease. And while societies decide what to do over longer timescales, then the camera drops underground. A tunnel is drilled through rock. The walls are dry or carefully studied. The rock is chosen not because it is dramatic, but because it is boring in the best possible way. Stable, predictable, slow. Engineers lower sealed waste packages into place. Barriers are stacked around the waste like layers of time. The fuel is in a solid form. It may be sealed in corrosion-resistant containers. It may be surrounded by clay or other buffer material. The repository is placed deep enough that ordinary surface events cannot easily disturb it. This is the idea of deep geological disposal. It is not based on one magic container lasting forever. It is based on multiple barriers. The waste form itself, the metal container, the surrounding buffer, the rock, the depth, the slow movement of groundwater, the chemistry of the underground environment, the distance from the biosphere. Each layer is there because no single human-made object can be assumed perfect for thousands of years. A canister can corrode, rock can fracture, water can move, chemistry can change. The design question is not, can we freeze time? It is, can we slow and limit the release of radionuclides so that any future exposure remains acceptably low? That is a very different kind of engineering. Most human structures are designed for years, decades, maybe centuries. A deep repository is designed for timescales that make normal architecture look temporary. It must be evaluated across climate change, erosion, glaciation in some regions, groundwater movement, container corrosion, and human intrusion possibilities. In an ordinary city, a building may be old after 100 years. In nuclear waste disposal, 100 years is near the beginning. Now, imagine groundwater. The camera moves through a crack in rock. Water seeps slowly along mineral surfaces. It does not rush like a river. It creeps. It dissolves tiny amounts of material. It reacts with metal. It carries chemistry from one place to another. In a repository, groundwater is one of the central questions because water is a possible transport pathway. If water reaches the waste package, if the package has degraded, if radionuclides dissolve, and if those radionuclides move through the rock toward the surface, then a future exposure pathway could exist. That chain contains many ifs, and each one is studied. The point of the repository is to make the chain difficult, slow, and diluted across enormous time. The rock is not just a container, it is part of the machine. Good geological setting can delay movement, trap radionuclides, or keep water chemistry stable. Clay-rich materials can slow flow and bind some radionuclides. Crystalline rock may rely on depth, engineered barriers, and careful understanding of fractures. Salt formations can slowly deform and seal spaces. Different countries study different host rocks because geology is local. The strange truth is that nuclear waste forces civilization to borrow time from the Earth. The radioactive clock is atomic. The storage strategy is geological. Now the image shifts to a warning marker on a barren landscape. A symbol is carved into stone. Around it, wind blows. The sun rises and sets hundreds of thousands of times. The language changes. The culture changes. The warning erodes. The danger is underground, but the message must survive above it. This may be the strangest design problem in the entire story. How do you warn future humans who may not speak your language, share your symbols, understand your technology, or trust your monuments? A skull and crossbones may not mean danger forever. A radiation trefoil may not be recognized forever. A warning monument might attract curiosity instead of keeping people away. A forbidden zone might become a myth. A marker meant to say, "Do not dig here," might one day say to someone else, "Something powerful is buried here." So the communication problem becomes almost impossible. Not only how to isolate the waste, but how to communicate danger through deep time. And yet the most reliable warning may not be a message at all. It may be depth. It may be geology. It may be the fact that the repository is placed where no one has an ordinary reason to dig. It may be records, institutions, land, use controls, and physical design working together for as long as they can, while the passive barriers continue after memory fades. This is why the underground scene matters so much. A repository cannot depend entirely on future people doing the right thing forever. It must be designed to remain safe even when active control is gone. The camera returns to the waste itself. Inside a canister, the fuel is quiet. The atoms are not. Some nuclei decay in seconds, some in years, some in centuries, some in thousands of years. Every decay changes the inventory. The radiation field changes. The heat changes. The chemical conditions may change. The waste is not frozen in one state, it evolves. This is one of the hardest ideas to hold in mind. Nuclear waste is not most dangerous because it is dramatic. It is dangerous because it changes slowly, and because some of the materials inside it remain hazardous long after the people who created it are gone. A person can understand fire because fire moves at human speed. A flood, an explosion, a storm, a collapsing building. These are disasters. Our senses can follow. Nuclear waste is different. Its most important motion can be invisible. Its time scale can be longer than a nation. Its safest place may be somewhere no one will ever see again. That makes it emotionally difficult. People want danger to have a face. Nuclear waste has isotopes. People want the story to end when the container is sealed. But the real story continues after sealing, after storage, after burial, after records fade. At the same time, scientific caution cuts both ways. It is misleading to say nuclear waste is harmless because it can be contained. It is also misleading to say all nuclear waste is equally catastrophic for all time. Level waste, intermediate. Level waste high, level waste spent fuel, reprocessing waste, contaminated tools, filters, clothing, reactor components. These are not the same thing. They require different handling because they have different hazards. The most difficult long-term problem is high level radioactive waste and spent fuel when it is treated as waste. It contains intense radioactivity, heat producing isotopes, and long-lived radionuclides. That is why it receives special attention. The camera moves through a reactor hall. Fuel enters as carefully manufactured pellets stacked inside metal tubes. It leaves as a chemically complex and radioactive material. Energy has been taken from it, but responsibility remains. The electricity may have powered cities for months. The waste must be managed for time spans no city government can personally experience. This is the central contradiction. Nuclear power produces a relatively small volume of high-level waste compared with the amount of energy generated, but that waste is concentrated and long-lived. Small volume does not mean small responsibility. Long-lived danger does not automatically mean unmanageable danger. The question is whether containment, storage, disposal, monitoring, and political decision-making are strong enough to match the material's timescale. The problem is not only technical, it is institutional. A canister can be designed, a tunnel can be excavated, a safety case can be modeled, but who decides where the repository goes? Who trusts the decision? Who pays? Who monitors? Who keeps records? Who explains the risk honestly without panic and without minimizing it? Deep geological disposal is not just an engineering project. It is a public trust project. Communities must believe that experts are not hiding uncertainty. Experts must be able to explain what is known, what is modeled, what is uncertain, and why the chosen design is expected to work. The camera shows a map with no words, only layers of rock, water paths, and buried canisters. The safety case is a story told in models. It asks, what happens if the container stays intact for a long time? What happens if it corrodes earlier? What if water chemistry changes? What if a fracture carries water faster than expected? What if climate changes the surface? What if future drilling intersects the site? What doses could result? How likely are the pathways? None of this can be proven by waiting 100,000 years before acting. So scientists use experiments, natural analogs, corrosion studies, hydrology, geochemistry, physics, and conservative assumptions. They test materials. They study ancient minerals. They model transport. They examine how radionuclides bind to rock or move with water. This does not remove uncertainty. It organizes it. The reason long-term disposal is difficult is not that scientists know nothing. It is that the timescale is so large that knowledge must be turned into durable design, and durable design must survive beyond direct supervision. Now the camera enters a microscopic world again. An isotope decays, a particle shoots outward, nearby molecules ionize. In living tissue, that might mean damage. In a sealed fuel pellet deep underground, it means another tiny step in the long transformation of the material. Radiation is only dangerous to people when exposure occurs. That sentence is simple, but it is the foundation of containment. The waste can remain hazardous for thousands of years without harming anyone if it remains isolated. The challenge is isolation, not for a day, not for an emergency response window, not for the lifetime of one building, for deep time. In the first decades, shielding and cooling dominate. In later centuries, heat declines and the concern shifts. In thousands of years, long-lived radionuclides and potential movement through groundwater become more important. The danger changes shape as time passes. A good management system must change with it or be designed passively enough that it does not need to change. That is why the best images of nuclear waste are not explosions. They are slow. A fuel rod shimmering underwater, a cask standing in silence, a tunnel being sealed, water moving through a crack, a warning marker losing its language, a future landscape above something no one can see. The true fear is not motion. It is duration. Now imagine the surface above a repository after the tunnel has been closed. At first, there may be fences, records, guards, maps, monitoring. A generation passes. The facility becomes part of national memory. Another generation passes. The original workers are gone. More generations pass. The landscape changes. Buildings are removed. Documents are copied, translated, archived, perhaps forgotten. A forest grows, or a desert expands, or ice returns, depending on the place and future climate. Below all of that, the waste remains in darkness. The canister ages, the buffer changes, the rock continues its slow chemistry. Most of the early intense radioactivity has decayed, but some long-lived isotopes remain. The hazard is not the same as it was on day one, but it is not gone. This is why thousands of years is not a poetic exaggeration. Some radionuclides require that kind of time before their activity drops to far lower levels. The exact hazard depends on the mixture of isotopes and the design of containment. But the time scale is real. When people say nuclear waste lasts longer than civilizations, they are pointing to the mismatch between atomic half-lives and human institutions. Human civilizations rise, split, migrate, forget, rebuild, and reinterpret the past. Atoms decay on their own clock. There is another misconception. If a half-life is very long, the material must be intensely radioactive. Not necessarily. A very long half-life means atoms decay slowly. The danger may come from persistence, toxicity, chemistry, and internal exposure risk rather than intense short-term radiation alone. A short half-life material can be far more active at a given moment, but it fades faster. A long half-life material may be less intense per unit mass but remains for far longer. This is why the waste inventory matters. You need to know what is inside. Cesium-137 is not plutonium-239. Strontium-90 is not iodine-129. Americium is not uranium. Each isotope has a half-life, radiation type, chemistry, heat contribution, and biological behavior. The waste is a mixture, and its hazard curve is the combined story of that mixture changing over time. The camera shows several clocks over the same canister. One clock spins quickly and fades. Another moves slowly. Another barely seems to move at all. The canister sits beneath them, not because it is a magical object, but because all these clocks have to be contained together. This is the engineering burden: to shield the short-term radiation, to remove the decay heat, to package the waste, to prevent water from carrying radionuclides away, to rely on geology after human maintenance ends, to keep the hazard from becoming exposure. The image returns to the deep tunnel. A canister is lowered into place. The machine moves slowly because speed is not the point. The tunnel is not a storage room in the ordinary sense. It is a carefully chosen section of Earth being asked to become part of a safety system. Around the canister, the buffer material waits. Above it, hundreds of meters of rock separate the waste from the surface. The canister's job is to delay. The buffer's job is to slow. The rock's job is to isolate. Time's job is to reduce the radioactivity. All four must work together. If someone says, "Why not just keep it on the surface forever?" The answer is that surface storage can be safe when actively managed, but forever is a very long operational promise. Surface facilities require institutions, maintenance, security, records, inspection, and social continuity. They can be part of the management chain, but they are not the same as passive final isolation. If someone says, "Why not launch it into space?" The answer is that launch failures, cost, and risk make that idea deeply unattractive for large-scale waste disposal. A rocket accident scattering radioactive material would turn a contained problem into an immediate contamination problem. If someone says, "Why not recycle it?" the answer is that reprocessing can recover usable materials and change the waste stream. But it does not make all radioactive waste disappear. It creates its own waste forms, costs, safeguards issues, and technical choices. Recycling can reduce some demands, but it does not erase the need for long-term management. There is no single sentence that solves nuclear waste. There is a chain of responsibilities. The camera moves through that chain: reactor, pool, cask, transport container, tunnel, sealed repository, geological layer, future surface. Each scene is calmer than the last. But the time scale grows larger. The danger is not getting more dramatic. It is getting more distant, more abstract, and more dependent on decisions made correctly, long before anyone alive in that future was born. This is why nuclear waste is so powerful as a story. It forces us to think beyond the emotional range of ordinary politics. A government can postpone a decision, a community can reject a site, a company can store fuel for decades, but the waste does not vanish during debate. The atomic clock keeps moving. Delay is not neutral. Sometimes delay is necessary for cooling, planning, consent, and better design. But endless delay becomes its own decision, to leave future generations with more of the burden. The scientific challenge is to isolate radionuclides. The moral challenge is to not pretend that temporary management is the same as a final plan. Now the opening tunnel returns. The canisters are still lined up. The camera pulls back again, but this time the images of the film pass over the tunnel walls: fuel rods glowing underwater, nuclei decaying, shielding doors closing, dry casks standing in rows, groundwater moving through rock, warning markers eroding, future humans walking above a place they do not understand. The tunnel does not answer them. It only holds. The most frightening thing about nuclear waste is not that it is impossible to understand. It is that it is understandable, and still difficult. We know why it remains hazardous. We know what half-life means. We know radiation can damage living tissue. We know shielding can reduce exposure. We know cooling changes the early risk. We know long-lived isotopes extend the timeline. We know geology can be used as a barrier. We know future communication is uncertain. The hard part is making all that knowledge last, because nuclear waste sits at the intersection of two kinds of time. Human time builds the reactor, uses the electricity, debates the policy, seals the canister, writes the warning. Atomic time keeps going after the warning is unreadable. In the final image, the surface is quiet, no reactor is visible, no tunnel entrance remains. The landscape has changed. Wind moves over stones that may or may not still carry a warning. Far below, inside engineered barriers and ancient rock, the waste continues its slow transformation. Many of the loudest isotopes have faded. Some long-lived clocks still tick. Nothing explodes, nothing announces itself. The danger is hidden in patience. And beneath a future world that may not remember us, atoms we rearranged are still trying to become something else.